and the first time they landed on the same day.
Oh,
great.
yeah, I remember because saw you dressed up that day.
Yeah, this time I get to be really dressed up. Yay.
Oh, they're making you really dress up?
Yeah, dress up like business professional. No.
Oh, all my idea said is wear a nice shirt and jeans, no sweatpants at all.
Yeah, that's what he said for the last one. And then this one, he's like business professional. I'm like, why do they keep getting worse?
Well, it's like, it was the middle of like spring, like that weird like slushy. Everyone's very done with college and stuff, and mine's like, yeah. If on your day of your speech, you can just wear jeans, nice shirt, but after that, you can wear sweatpants. So it all depends if you wanted to go first and just get out of the way and wear sweatpants, or you play the game of roulette. Because she always did a randomized name pick.
Oh, okay. Yeah.
So you play roulette and hope you get 1 extra week. Do it.
Hell yeah. Hey, cool. Happy to see you again. Thanks for staying committed for the course. I don't know, voluntarily or involuntarily. So, who we are, where we are, and what are we doing? Physical chemistry, characterization of materials as a far-going goal, quantum theory as what we practically do, anything that vibrates, very, very narrow thing to discuss. And it's always interesting to look on time-resolved phenomena, but you cannot go to any dynamics before looking on static properties. So therefore, we have completed development of eigenstates of oscillator. We did it through this trick of ladder operators, and it would be logical to move towards the dynamics. So having things that Austin has already presented on last Friday, with more details and with theoretical background. Yes. But without any bad intentions, while going to this reasonable goals, we always realize that there are technical things to cover before we go to the goals. So about next meeting, or maybe Monday, we will go to oscillation of oscillator. And today we are going to establish a bridge between static solutions, between eigenstates, and practical approaches to dynamics. So the word dynamics will not be pronounced except this second, but it will be another little technical trick which will make you masters of space and time in respect to humble harmonic oscillator. What do we have here? Ladder operators in discrete representation. So from not long ago, there is no intrigue in piece of information that any quantum operator can be thought as a matrix, right? And these matrices can be cast in different spaces. One opportunity is to cast a matrix that represents an operator directly in discretized position space. It is what you guys presented in last session of presentations. Andrew, who is missing today, and at least now, was computing these operators represented in the Cartesian position space. But London readily kicked back a challenge from a visitor, answering on all questions about momentum space. So the same operators can be represented in momentum space. But one of the most comfortable spaces where operators can be cast as matrices are spaces of eigenstates, because there are, even if they are, there is infinite number of states, they are discrete and countable. And right now we do have concept of ladder operators for quantum oscillator in the Cartesian space, but it would be really reasonable to nail them down and be able to describe everything in the space of eigenstates, where each eigenstate, each eigenfunction is like a point in a space. Make sense? At the end of the meeting, you'll have a matrix with everything populated with zeros except few elements, and it will be representation of creation operator in the space of eigenstates. If you're fine with this idea, now you can just pull back and relax a little. Prepare to your to the next step in your busy schedules. I'm using our today's meeting also as relaxation because I have impressively busy schedule after this meeting. So let's relax together with quantum mechanics. I have forgotten to print, but hopefully the electronic form is enough. You have the PDF versions or PowerPoint versions of the things. So please try and bring handwritten or printed versions of the homeworks by Friday. If you want any other form of distributing homeworks, just raise hand or send me an email. It's some sort of my responsibility to deliver the things. So here is where we stopped last time. And so applying creation operator to an eigenstate of harmonic oscillator, we immediately here I made a mistake. Anyone wants to catch it? The mistake is in most important yellow background, red box.
Should be 5 n plus 1.
So by applying it to the eigenstate of a given index, we go to the next eigenstate with accumulated factors. Okay? And in some sense, we are not going to anything new compared to this line. We just looking on the same expression from different angle. If we do it again and again, it will be easier later when we use it practically. So no new information, just looking on available things from different angles. Oh, what are we going to do in the labs if anyone elects to come today? So long time or midterm or no midterms. I feel scared when I hear this word, like midterm or final. No. Intermediate range of time planning in the future. What are we going to do in the labs and in the class? You already got enough skills to start independent research projects, which will be part of the class. And I will soon develop a list of subjects that you can choose from, or you can design your own research project. The plan is it will most of the problems can be projected on one-dimensional propagation, like 90%. So you just may want to design a problem or select from the list. So in the nearest future, we will practice democracy plus creativity if you come up with your own ideas. One of the problems for independent projects can be something that related to the question that Christian asked to Beth in the last minute of the presentations. Use of finite box for redox reactions. Redox reaction for one molecule is boring. If you are chemist, true chemist, then you may have practiced electrochemistry when the oxidation and reduction of a molecule is induced by placing it in a solvent near electrode that has different potential. So if I'm just showing opportunities. If one electrode molecule, you will coordinate, the height here will be either reduction or oxidation energy, like ionization or affinity. And then, what do you do on the redox experiment? You change, you know, what are electrochemistry experiments?
Potentials.
No, I'm asking London specifically because I know that his major is not in chemistry.
What was the question again?
Electrochemistry, what is it?
Well, I know like
There's
generally speaking,
electricity
like
in
what
chemistry.
electronegativity is, I
Yes.
guess, of like a molecule, I guess. It I don't know, something about lining up like the dipoles of molecules to I don't know.
It is,
I can guess.
It's converting chemical energy to electrical energy and vice versa.
Oh, okay.
yeah, you can say so. In some sense, it is related to the photoelectric effect.
Okay.
But here, the driving force is not a photon, but applied voltage. So there are electrodes, positive and negative. A molecule sits near one of the electrodes or just in a solid. And then now I will tell something on the language of a physicist. If there is a electric field, then the potential, the background potential for anything we drive will get a slope. So from this picture, so if the molecule used to have an electron, this driving force will make it to transfer the electron density to the electron. If you apply the potential in a different direction, then even if molecule didn't have the electron, it will have this driving force. The electric field will drive an electron density from the electrode to the molecule. So you can do tricks like this as a part of the independent research project. And it is one of the 15 I will offer you to decide. Just giving you to unleash your imagination for the background thinking. True chemists may appreciate problems like this.
So basically a CV graph where you put in energy one way, you get a peak, and then when you taken away energy, you get a reduction peak. And then peak.
Yep.
Okay.
And the knowledge and practical skills that you got in this course are already sufficient to get these curves in approximate fashion.
Okay.
For exact things one needs to do atomistic, computational chemistry, but for proof of concept, you guys already have very solid background. Before this practice of democracy and creativity. There are several subjects that we will cover in the labs. They will be not new in a sense of theory and background. It will be a little introduction to different aspects, what can be modeled with this one-dimensional propagation. For example, last time we missed the transmission coefficient that we may want to work out together. Right now, this ugly big box is a chunk of metal electrode. We can cover how to model solids like electrodes or semiconductor quantum dots a little bit more precisely by making individual dips for each atom. So, and there is another thing that I hope you will be able to cover in the labs. Not everything today. It will be spread over the remaining time plus projects. The Marcus theory of electron transfer. Did you hear about it? No one? Okay, then I will have pleasure to introduce it to you in about 2 weeks from now. But it is a theory that was worth of Nobel Prize 60 years ago. And it is really helpful for, again, redox reactions in solids. Again, after little relaxation is quantum mechanics, today we are going to model dynamics. And most intuitive understanding of dynamics, if by some reason the oscillator is removed, disturbed from equilibrium, in classical analog, just kicking it with non-zero momentum or deviating it from the equilibrium, like elongating or contracting. So we will look for expansion coefficients in the basis of eigenstates that will correspond to such displaced state. So there's a plan for maybe 3 minutes from now on. And then we'll see what will go on. Okay. So this is a standard thing. Oh, it's time to focus on the screen. If anyone wishes, if not, it doesn't matter. So we will practice. It will be reasonable to practice the standard eigenstate expansion, where the displaced state, non-equilibrium state, is represented by a set of expansion coefficients. Each state evolves in time according to the accumulation of phase, its eigenenergy, and then we get state function, wave function of the system of our choice, of oscillator, in the non-equilibrium state, which will experience some motions, and hopefully things that Austin presented last Friday will be confirmed. Maybe not. We'll do an experiment. Okay. So square root is somewhere here. Is it multiplying by square root or dividing by square root?
Multiplying.
I hope so. So, and I do have my cheat sheet, just in case. Close the eyes. Yes, you were right. So, the coefficients in front, and we can continue this progression. If you apply it once again to second, we get square root of 3 by 3. Do appear from normalization factors. So if you find result of action, or you find a function that is assumed to be an eigenfunction of a quantum problem, it is, for additional safety, it is always reasonable to normalize it. Check that the coefficient in front upon absolute value square integration gives 1. And through this operation, we are developing this square root factors. In some sense, by now we do have any excited state, any eigenstate of the oscillator, right? So we can tell that first one is creation applied to ground state. The second one is creation applied to the first one divided by square root of 2, or a creation applied 2 times to the ground state. And the third one is creation applied to the second one, or 2 creation operators applied to first one, or creation operator in power 3 applied to ground state, and here we have 1 times 2 times 3, right? So applying creation operator n times, we are promoting the ground state into desired excited state. It is a little, not little, it is substantially easier than making recursion and series expansion for solving this problem. So we already have the benefit of regular practical way to fabricate, generate, find any eigenstate of the harmonic oscillator. Later, very soon, when we will explore dynamics, we are going to use space of eigenstates. And if we will be staying in the state of in the space of eigenstates, space of eigenstates, then we may want to express everything in this space, including all operators. So ladder operators, position momentum operators, kinetic potential energy, total energy, whatever. We probably will never return back to Cartesian space for operators, but if you would realize that it is much harder. So through new concepts, we simplify our path to the desired goal. So in space of eigenstates, express all operators. Express all operators. I think it is a verbalization of what we were discussing. If you're watching recordings, here is the text to read. I'm going to write something without introduction, and then based on your feedback, which can be either supportive and like, okay, I know it, or surprised, like, you didn't warn us. So based on your eyes, I will decide whether I need to express verbally what I'm doing. So any operator, including the equation operator, can be represented in a given basis with matrix elements. Okay, now I'm interested to see your feedback just in the verbal form. I do not see big protest, but I do not see big joy. A couple of years ago, there was a Olympic Games, and one of them, I think it was a lady who won silver in gymnastics, and she had a expression like skeptical, not impressed, of her own award. I see the same faces on you. Like, maybe not terrible, but I'm not impressed. Too many words for this simple expression. So maybe because this stuff blocks. Angela, can you please move this thing to the other side, if it is easy? So it is here, m times bra n. Okay, thank you. And now we can select this m and n being eigenstates of harmonic oscillator. Phi m, phi n of any order. And the matrix elements is what we need to find. Basically, this construction, what it does, if it is applied to arbitrary wave function expanded in the same basis, it will convert it into something. But what we are, these brackets are Dirac notations for rows and columns, right? And they serve as a bridge between space of functions and space of vectors. Okay. The goal for us is to write something more specific here. So if you have phi n, this dagger operator converts it to n plus 1. Or it can create this phi n from phi n minus 1. So the operator, this creation operator, serves as a delivery man, as a postman that can deliver mail not everywhere, but only between nearest neighbors, only from one door to the next door, right? So it will do something only if one state and another one are equal in everything but one index, but one number, if they're neighbors. Okay? And it collects a phi. Post. Selfish postman. Doesn't work for free. Okay, so what is your non-verbal reaction? Okay, I see a little encouragement, like, okay, go this way.
I have one verbal question.
Please, please.
So we talk about the N and the like as a state. What's the M for? Like you have the cat portion.
Very good. Thank you. We want to develop something universal. So if we are telling that operator is a matrix, it will be square matrix that where indices of row and column run for the whole space. And we need two independent indices, M and N, or you can select some other letters like alpha and beta or L and K. And they need to be different if we, unless we know that the operator will be diagonal, right?
Mm-hmm.
Therefore, we need independent index for this cat.
Okay.
We are going to simplify it and remove it, but for generality, we want to have it. If we will have some different operator, not raising ladder, it could be anything. Here, through this delta function, we see that there will be most of the matrix elements will be zeros. But in general case, there is no theorem that most matrix elements of an arbitrary operator must be zeros. So it is the reason why the academic courses focus on simple systems, because they're highly symmetric, very simple, and things like this happen.
Mm-hmm.
If you go to real world, then everything will be non-zero and not possible to express in simple functions. So we are getting through the concepts by very simple examples that a regular human being can go through with pen and paper. All or vast majority of practical problems are not possible to do by pen and paper. Okay, I didn't lie. It is the same thing as I prepared on the cheat sheet. So, what do we do next? We are going to get rid of M. Get rid of M, because we know that M O is equal to N plus 1, right? So we replace M into N plus 1. So we do have summation over N, summation over N, so N plus 1, delta, N plus 1, N. Right? It is what we had on the previous one. If we commit the replacement, if we M goes to N plus 1 and N is replaced to N minus 1, if you need to do it. N plus 1. What will happen if a summation sign does observe the delta function sign?
You're just going to be left with the one index.
Yes. So summation and delta function cancel each other. It was my major discovery when I was sitting in the same kind of undergraduate class, and I was hearing it like 3 times before I started to agree and applying. And final step that convinced me that summation sign and Kronecker delta cancel each other. So summation is like a snake, and the delta is either a mouse, and or if you like drawing, you can consider it as a rabbit with 2 ears. I don't know, but they both disappear. Like summation, summation is being fed by delta functions. So instead of m, we will have n plus 1. The delta function disappears, and the summation disappears. So
The other sum should disappear.
yes, right. Correct. So now you are experts in algebra of operators. Okay? So after removing the things, we do have transition from n to n plus 1, and the matrix element is nothing but square root of n plus 1. Good? So I'm going to speak for another 10 minutes, but I'm not going to tell anything new. I'm going like walk around the same spot again and again, maybe clockwise and counterclockwise. So you will see nothing new. You'll see the same information as we already discussed, just from the different angle. So suppose we believe in this expression. N plus 1 is two advanced calligraphy. Now, if we want formally to develop matrix elements, just by definition, by blind routine, we need to take the operator and multiply it by states basis functions from bra and cat from left and right. So the operator is not a number, but if you convolute it with bra and cat, it becomes matrix element. It becomes a number with 2 indices. A without head with 2 numbers k and l. So what if we apply multiply our top line by bra from left and by cat from right? Just a little notation to avoid confusion. As a tribute to laziness, I just skipped the symbol phi. So this like k or l, the R stand for function or wave function conjugate, right? So if you feel confused, you can write the symbol here everywhere. very good. Just take an extra effort on your hand. If you take notes. If you don't take notes, then you do not care. So what will happen after we apply the Brian cat eigenstates from left and right? Here it will be just delta function. No. Here, okay. This one will become delta function of L n plus 1. And
That one should be a delta of k and n plus 1, shouldn't it?
correct. Yes, thank you. Okay, n plus 1. So one summation will be removed, and we will come back to the expression that it will be between n and n plus 1. And one index will stay. So through this operation and orthogonality, we can come back into the expression for matrix element. So we just went forward and backwards in these notations. In fact, we assumed this form from the first place. We knew that it will be this way, so we didn't. It's not our finding. We just check that you can come back to it. So through formal protocol to get matrix elements, we can take our algebraic Brian-Cat form of Christian operator, plug it between sandwich of Brian-Cat, apply orthogonality, and get the matrix element, right? But it is not new. And it is fine if you split me and taking relaxation. So this is a record of a matrix, right? And we can agree that first index will stay for index of a row, and second for index of a column. And then due to this delta function, you will see, like, if it will be no plus one single, it will if matrix is equal to delta function, it means that only main diagonal is non-zero, right? It's 1, 1, 1, 1, 1, and the rest is 0. If you have this plus 1, it means that the index of row must be larger than index of column by 1, and only then the matrix element is non-zero, which means it will be subdiagonal. So main diagonal will be 0, but a thing below it will be non-zero. And if you would not have this phi, this factor, it will be just 1, 1, 1, 1, 1 below main diagonal. With this, it will escalate as we go further and further away from the origin, from the element 0, 0. Make sense? Let me try to sketch it. So if we grow rows by m and columns by n, then we will have zeros on the main diagonal, we already agreed, and here in element 0, 0, this element 1, 0. So here number of row is bigger than number of column. So here we'll have non-zero value by 1. Here element or index of row is bigger than index of column by 1. So here we have something non-zero. And the rest are zeros. So sub diagonal. Right? And we can populate it by square root of 2, square root of 3, square root of 4, and so forth. So this matrix will be matrix representation of the equation operator in the space of eigenstates of harmonic oscillator. Right? So I will mumble a couple of comments in addition, but I think it is enough for today, and time is coming to completion. So all operators, including position, momentum, kinetic, potential, and Hamiltonian, can be expressed in terms of the equation operator. The annihilation operator is just the conjugate, which means that we will just transpose it. So we flip it along the main diagonal, and then here you have zeros, and here you have square roots, right? And then we plug them into linear combination that converts ladder operators into normal, regular operators, and then we will be able to do everything in the space of eigenstates. This will make our attempt to predict quantum dynamics especially quick and pleasant. Well, it's not the best pleasure in the life, but much more pleasant than it could be. Please consider to bring hard copies of the homework on Friday, and enthusiasts of quantum dynamics are invited at 5 p.m. to the MATLAB modeling of quantum dynamics. Meeting is over. Dismissed. Stop by and ask questions if you know some.